In this video, we're going to create a quadrant system in Unity ECS. A quadrant system helps us group nearby units into quadrants. That allows for massive performance for any algorithm that requires finding neighbors, since we don't need to cycle through every single entity, but rather only the ones nearby. Let's begin. Hello and welcome, I'm your Code Monkey, and this channel is all about helping you learn how to make your own games with in-depth tutorials made by a professional indie game developer. So if you find the video helpful, consider subscribing. So over here we have the final system that we're going to create. I've turned on debug lines so we can visually see each quadrant. As you can see, when I pass the mouse over, the world is clearly split into separate quadrants. There are units and targets being spawned all over a very massive area, and all of those units are searching for their closest target. Now, without using the quadrant system, where we have 10,000 units independently looking for 10,000 targets, you can see that we are taking 56 milliseconds per frame. However, with enabling the quadrant system, which ensures that the units only look for targets nearby, by enabling, we go down from 56 all the way down to 14 milliseconds. So essentially a unit all the way over here will never even search for a target all the way in here. So you can see the massive performance benefits of using such a system, especially when you have a lot of units spread out over a very large area. Now in here I am demonstrating a find target algorithm as a way to view the benefits of a quadrant system, but it can really be applied to any sort of problem. The way the system works is by first placing the units and targets into their quadrant based on their position. Then for each unit we search the nearby quadrants for targets and only those in the nearby quadrants. So this unit in here will search the nearby quadrants, but will never test the position of the target all the way over here. So that's exactly what we want, since if the target is too far, ignoring it only makes sense for performance. Then when the unit finds the closest target, it simply adds a component which moves it towards the target and destroys it. And as you can see, all the units in this massive world, they're all looking for targets, moving and destroying. And in here with 10,000 units looking for 10,000 targets, we are getting some very good performance. Alright, so this is our goal, let's get to it. So here is our starting scene. Now this starting scene here is the scene from the Find Closest Target video that we did previously. So if you haven't already, go check out that video. Again, I'm only using the Find Target as an example algorithm. This is just one of the possible use cases for the quadrant system. It can be used to solve many other problems that require knowing nearby entities, like for example, Obstacle Avoidance. Essentially, we have units and targets being spawned, and the units are looking for the targets. However, right now they are currently looking for every single target regardless of how far it is. So this unit down here is cycling through all of the targets all the way up here. This is obviously very inefficient. We should limit our cycles as much as possible and only cycle through targets that are actual potential targets. So let's see the code for how all of this is set up. Here is our main script. Again, the starting point here is from the Find Target video, so you can see that to see how we got here from scratch. We have essentially two archetypes, one to spawn a unit and one to spawn a target. They are differentiated by these two tag components, which you can see down here. They are placed randomly, and then we spawn a bunch on the start and a bunch every so often. Then we have the Find Target system. This one has a bunch of jobs to cycle through each target and find the closest. When he does find the closest target, he adds the hasTarget component with the target entity. This component only holds the target entity. And then we have this system right here, which runs on entities that have a target and simply moves them towards the target. Alright, so this is our basic setup. Now let's begin writing the code for our quadrant system. So in here, let's start off by making a new C# script for our quadrant system. Now in here, get rid of this, and instead of a mono behavior, this will be a component system. Now in here, we're going to have a bunch of jobs to place our entities into their respective quadrant. But first, let's think of how we're actually going to store a quadrant. We need some way to have multiple values per a single quadrant. So for that, we can use a native multi-hashmap. This collection lets us have multiple values per single key. So that's great. Now all we need is a way to get a key for each quadrant. Now there are many ways to calculate keys to put positions in various buckets. Let's make one that returns just a simple int. So our multi-hashmap will be composed of keys based on an int, and it will hold entities. So let's make a function to calculate the quadrant. I'm going to make this a private static. It will return an int, and let's call it get position hash map key. In here, we'll receive a float3 for the position, and we want to return the hash map key related to this position. So in here, we're just going to use some simple math in order to create some very simple squares. Alright, so here we have a simple function. Essentially, we are flooring the x and the y based on a certain quadrant cell size, and for the y, we are simply multiplying it by a certain value. So for example, an entity on 0, 0 will have a key of 0. However, an entity on 60, 0 will have a key of 1. So this function will essentially convert our position into a nice hash map key. Now, in order to visually see this, let's make a nice debug function to draw each quadrant. Okay, so here it is. Now all we're doing is essentially just drawing 4 lines in order to draw a square for our quadrant. So we calculate the lower left vector, which is doing the exact same math as up here. We just do a floor on the x and the y. And then we draw a line from the lower left into the lower right, then on the upper left, and so on and so on. So now let's test this. Down here on our update, let's draw it on the mouse position. So a debug draw quadrant. Now in here, let's draw it on the mouse position. So for that, I'm going to use a function from the CodeMonkey utilities that you can grab for free from unitycodemonkey.com. So using codemonkey.utils, and then simply use the utils class to get the mouse wheel position. Okay, so just like that, we should be able to see all of our quadrants. Okay, so here we are. Now, first of all, since we're using the debug.drawLine, we need to go up here in order to enable gizmos. And now in here on this scene, we are using a very small camera size, so let's modify our quadrant size. In here, instead of setting the quadrant cell size at 50, let's just put it at 5. So here you can already see the quadrants being drawn. Let's zoom out a bit. And there it is. Okay, so this is one quadrant, as you can see, and as I reach the edge, there's another quadrant. And in there another, and down here you can see the values that are automatically calculated. So this one has a quadrant hash key of 0, this one a hash key of 1 and 2, and this one is 0, and above it is 1,000, down minus 1,000. So essentially we have a nice unique hash key for each position in our map. So just like that, we have separated our entire world into various quadrants. Now what we need to do is actually put these objects into the quadrant that they belong. So for example, this unit here would be on this quadrant, now this one, and so on. So in order to place our entities into quadrants, let's start off by making this very simple and using simple single-thread code, which we'll later convert into jobs. So in here, let's simply cycle through all entities and grab their position. So with translation, we can get the position hash map key, and we pass in the translation.value. So we calculate the hash map key based on the position of this entity, and now we simply add it to the hash map. So before, let's instantiate our hash map. So we create a new one. Now in here, we need a capacity. In this case, we're going to fill it up with all of our entities. So let's calculate how many entities we have. So we calculate the length, and then we create it using allocator.tempJob. And in here, we simply go into our hash map in order to add, pass in our hash map key, and let's store the entity. And that's it. We now have our entities being correctly placed into their specific quadrant. Now to make sure that this is working correctly, let's make a function to count how many entities are in a single quadrant. So let's make a private static int, call it get entity count in hash map. Now in here we receive our native multi-hashmap. Then we also receive an int for our hash map key. So we want to return how many entities are inside this key. Now in order to get the values from the multi-hashmap, we need to use the multi-hashmap.tryGetFirstValue. So this one receives a key, so our hash map key. Then we need to pass in a variable, which will be the out parameter for our entity. So we pass out entity into that variable. Then we also need a native multi-hashmap iterator. And just like that. Now this returns a boolean if we have a first value inside this hashmap key. So if we do have a first value, let's test if there are more values. So in here, let's do a cycle, a do while. So we're going to do something while we still have values. So in order to test, we do a try get next value. In here, we pass in the same out for our entity and a reference to the same native multi-hashmap iterator. So this cycle will keep running for as long as there's entities inside the same hashmap key. So in here, we can just simply define an int for our count, start off at 0, and here increase it, and out here we return it. All right, so we have a nice simple function cycling through all the values inside our hashmap and returns the correct total. So this is how you iterate through a native multi-hashmap. Essentially, you try to get the first value and then keep getting the next value until there are no more. All right, so let's test this out down here. Let's still draw our quadrant, and then let's do a debug.log of our count. Then we get the position hashmap key of the current mouse wheel position. So we should be able to see in the log how many entities are stored in the quadrant right beneath the mouse. Then here, since we're dealing with a native multi-hashmap, we need to make sure to dispose of it in the end. Okay, so let's test. Okay, so here we are, and let's see if it is correct. We can already see the current quadrant being highlighted, so this one and then this one. So now let's go to the left, and here on the log we are seeing 2, and indeed we have 1 and 2 entities. Now let's see this quadrant down here, and we have 4, and yep, 1, 2, 3, 4. And in here we have 1, 2, 3, and yep, exactly correct. All right, awesome. So we have successfully created a quadrant system to place our entities into various buckets. Now that we have this code working, let's improve upon it. So the first thing is obviously convert this into a job. So let's go up here in order to make a struct. Let's call it the set quadrant data hashmap job. So we're going to set the data for each quadrant, and it's going to be an I job for each with entity. And we also want the translation. Now in here, we need to receive the native multi-hashmap. And since in this job, we are going to be assigning values into our hashmap, we need to pass in the .concurrent in order to be able to concurrently write to the same hashmap. Now on execute, we're going to do the same thing we were doing down here. We calculate the hashmap key based on the translation, and then we simply add it into that key, this entity. So that's it. As you can see, very simple. And finally, we can just very easily add the burst compile in order to make this even faster. So now down here, instead of doing our for each, let's create our job. All we need to do is pass in our quadrant multi-hashmap. Make sure you write to concurrent. And in here, we can schedule our job. Alright, so that's pretty much it. Our code should still be working exactly the same as previously. However, right now we are benefiting from multi-threaded code. Let's see. And yep, there it is. Everything still works normal. This quadrant has indeed 2 entities, this one only 1, and yep, everything is working correctly. Let's see just how quickly this job runs. So let's disable our debugs and spawn a lot more units. Okay, so here we have 1,000 units and 1,000 targets being spawned. And if we check out the stats, you can see that all of them are being placed in the correct buckets into their native multi-hashmap. And as you can see, the whole thing is only taking 1 millisecond. So thanks to using jobs, this system is insanely fast. Okay, so right now we are only storing the entity. That works, but if we need more info from that entity, we're going to have to do an expensive call going into the entity manager in order to get the component data and so on. So we should really find a way to store more than just the entity into our quadrants. So here in our quadrant system, instead of having a native multi-hashmap of entities, let's go up here in order to define a very simple struct. Let's make a struct and call it quadrant data. Now in here, let's start off by simply our entity. And now we modify all of our function calls in order to work with a multi-hashmap of quadrant data. So in here, when adding, we need to create a new quadrant data. In this case, we just pass in the entity. All right, so we now have our native multi-hash map working with a specific struct. So we can go up here and add as many values as we need in order to work with our quadrant system. So for example, let's add a float 3 for the position. So down here, when we add it, let's also add the position, which is the translation.val. So just like that, we have made our code more robust by making it work with a specific struct instead of an entity. So this way we can clearly define what data we're going to need for our quadrant system. So let's run the code just to make sure everything still works. And yep, everything is still working, and it's still working insanely fast. Now another improvement we can do is to only place certain entities into our quadrants. So right now we're running this query, which is simply searching for entities with translation. So any entity we create, as long as it has the translation, it's being added into the quadrant system. That can be quite wasteful if you have a bunch of entities that are not intended to be used by the quadrant system. Like for example, if you had entities for a particle system. So let's make a very simple component to define which entities should be placed. So we can go up here in order to simply make a struct for a component. Let's call it quadrant entity. So we're only going to work with entities that have this component. Now an empty component works perfectly fine. However, we can also set more information in here. So for example, we can store a type. So here we're defining two types, a unit and a target, and we're storing that on our quadrant entity. So let's go to when we are instantiating our archetypes. In here, we also add the type of quadrant entity in order to make sure it gets added into our quadrant system. Then we set the component data just like that. So we add our component in order to be used by the quadrant system, and we pass in the information that is needed. And now in here on our quadrant data, we can also store a quadrant entity. So all we're doing is adding all the information we're going to need in order to be stored per each entry into our quadrant system. So down here, when we add our key, let's add this as well. Okay, so now our set data job now receives a quadrant entity, which we're going to use in order to add to the hashmap key. Now down here, our entity query is no longer just a translation, but the translation and the type of quadrant entity. All right, so that should do it. So we can now add this component to any entities that we want to be used by this quadrant system. And we have a lot more information being stored per each entry into each quadrant. Let's see. And yep, everything's still working perfectly fine, and it's still pretty fast. So again, everything still works, but we can now easily define which entities should be placed in quadrants and which should be ignored. Now another improvement we can make is regarding the native multi-hashmap field. So right now we're creating and disposing of it on every frame. Now this works, but obviously means we no longer have our quadrants once the system is done. Meaning if we want to use this quadrant system by another script, we would have to add all of the related code in here. So for example, our find target code would have to be placed right here instead of being in its own specific class. So instead of doing that, let's make this a permanent native multi-hashmap. So we can simply do a override on the onCreate. Now we're going to create a native multi-hashmap, and we're going to define it as a static variable. So we have our static quadrant hash map, so that can be used by other scripts. Down here we instantiate it very much in the same way, except for the allocator we use persistent. Then let's also override the onDestroy in order to make sure we dispose of it. And now we no longer need to do this in here. Okay, so let's run the code and see. And just like that, we have an error right away. This tells us that our hash map is full. That's because the hash map cannot grow dynamically inside a job. So we need to make sure we give it the correct capacity before running our jobs. So in here, we need to expand it to fit. So we check if the entity query calculate the length. If that is bigger than the quadrant capacity, then let's expand it. In order to expand, we just set the capacity to be the new length. And that's it. Just like that, our quadrant multi-hashmap will now expand to fit whatever it needs. And since this is persistent, we need to make sure to clear it. So before we do this, let's clear the current hashmap. All right, so let's try again. And yep, here it is, and our code is working fine, no errors, and everything still works. Okay, awesome. So everything still works the same, except now we have our hashmap, which is accessible from other systems. So now let's finally apply this to our find target code. Here is the find target system. Again, this system was made in a previous video, so check that out to see how it works. So in here, we are essentially going through every single target. We have the find target job, which in here cycles through every single target and sees how far away it is. Now let's do this by cycling through the targets only in a single quadrant. So let's make a private struct, find target quadrant system. Let's copy paste this target as our starting point. Now in here, we no longer receive an array of targets, but rather we're going to receive our native multi-hashmap. In here, we calculate the hashmap key based on our translation. Then we cycle through the entities in that hashmap key. So here we are cycling through all the values inside this hashmap key. So it's in here that we need to find the target. So use the values that we stored in our quadrant data. So we stored the entity and the position. And that's it. So we have a very nice job looking for targets, but only looking those that are in the same quadrant. One thing we also added in our quadrant data was the quadrant entity. So in this case, we only want targets that are of different quadrant entity type. So essentially, we're going to only search for targets that have a different type enum from this one. So the type enums are the unit or the target. So the units will look for targets, and if we wanted, we could also make the targets look for units. All right, so now let's replace our job down here. For the multi-hashmap, we pass in the one that we have our reference on our quadrant system. All right, that should do it. Let's test, and we should now have units looking for targets only in their quadrant. So let's see, and yep, they are correctly finding their targets and moving towards it. And these right here are static, meaning they no longer have targets inside their quadrant system. So you can see that they are only searching for targets inside of their quadrant. All right, so obviously it worked, but you can already see the issue. Right now, the targeting range is limited by the quadrant size. So this target right here is outside of the quadrant, so these two will not find it. So this is a problem with a lot of different solutions depending on how fast or accurate you want your targeting to be. Now in this case, we can simply increase the quadrant size by a little bit and make sure our units search for nearby quadrants as well. So here, let's put this code into a function so we can easily check the nearby quadrants. Alright, so here we have put our find target code into a separate function. You receive a hashmap key so we can easily check the neighbors. Let's just make sure that this is still working the same. And yep, okay, everything's still working the same. Look at these two looking for targets, and they don't search for those since they are far. And yep, exactly. Okay, everything's still working. So now in here, we can easily check for all of the neighbor quadrants. So first we check the one on the hashmap key, so that's the one that he's in. Then we check the one to the right, which is +1 on the index. Then we check on the left, so it has a hashmap key of -1. Then we check above, so it's plus the quadrant system dot quadrant y multiplier, that's the one above, and the minus will be the one below. Again, this is all based on how we calculated our hashmap key. Now for the corners, So here we are searching for all of the targets in the neighboring quadrants. And here in our quadrant system, let's also increase the cell size by a little bit. Okay, let's test. And okay, here we are, and all our units are searching for targets. And as you can see, they are searching for nearby quadrants. Look at that one. So for example, that one finishes those 3 targets, and now they're going to search for the ones on the quadrant next to it. Alright, so our units are now looking for targets on more than just their quadrant. So the targeting is now a lot more accurate. And as you can see, our frame rate is still pretty much the same, only taking 1 millisecond. So now let's see exactly just how fast this is. Let's make sure they keep looking for targets. So let's stop adding the component in the end. So on our add component job, let's not add the component. That way they're gonna constantly keep looking for targets. And let's modify the code in order to enable to test both methods. So here we have 10,000 units being spawned over a massive area, along with 10,000 targets. And as you can see, it is taking 70 milliseconds in order to find the closest. So every single one of those 10,000 units is cycling through every single one of those 10,000 targets. So obviously that is very wasteful, since a unit down here doesn't care about a target all the way over here. So now let's enable the quadrant system. And there you go, we went down from 60 all the way down to 15 milliseconds. So right now this unit down here doesn't care and doesn't even try to search for this target over here. So the units are only searching for targets in their quadrant and the ones nearby. Now again, the find target is just one possible use for the quadrant system. The whole point is placing entities into smaller separate buckets. That way you have much faster searching for whatever it is you want to do that relates to entity positions. For example, you can make a unit avoidance algorithm. Just search for the closest entity in the quadrant and see if it is close enough, and if so, stop moving. The possibilities are endless, and this is a great system to apply to many different problems. As always, you can download the project files and utilities from unitycodemonkey.com. If you liked the video, subscribe to the channel for more Unity tutorials. Post any questions you have in the comments and I'll do my best to answer them. Alright, see you next time.